Hi, I'm Pierrick, and I will give you a brief overview of our paper, Attributes Shape the Embedding Space of Face Recognition Models. In this work, we study how attributes like hair color or lighting affect the embedding space of face recognition models. First, a quick recap of a typical face recognition pipeline. An image is taken and passed through a face detector, giving us a bounding box and facial landmarks. The image is then cropped, aligned, and embedded into a vector space called the embedding space. Learning the embedding function is usually done with a contrastive loss, where triplets are composed of an anchor, a positive example, and a negative example. The optimization objective is then to pull the anchor and positive example closer, while pushing the negative example away. In face recognition, the label is simply the identity, a transitive relation, and so the learning process should intuitively lead to identity cluster in embedding space. And indeed, in practice, we observe two scales in the embedding space. At the macro scale, we see a point cloud of identity clusters, one per identity. At the micro scale, when we zoom on a single cluster, we see different images of the same person. Another observation is that the impact of attributes depend on the scale considered. For example, as illustrated here, gender on the left influences more the macro scale, while illumination on the right affects micro scale more. So the question we address is, what is the influence of attributes on the embedding space? We will study it at the macro scale for binary attributes and at the micro scale for continuous attributes. Let's start with the macro scale, where each point is an identity. For this analysis, we use celeb A, a dataset of real images with binary attributes like gender or eyeglasses. We propose to look at the separability of attributes in embedding space. To do that, we quantify how much the modalities, represented here by the two colors, are cleanly separated in embedding space. We estimate separability by comparing the distribution of distances within a modality with the distribution of distances across modalities. We find a significant impact for the majority of attributes. But to go a bit further, we also asked why are some attributes more separable than others. We find that attributes with higher discriminative power are also more separable. Discriminative power is approximated by an anthropic measure, and as an example, gender would be more discriminative than smiling since it gives more information to identify the face. Interestingly, models agree on which attribute matter most, but differ in the magnitude of the separation. Now let's go on with the microscale, where we look at continuous variation for a single identity. For this part, we rely on generative models to control the design of faces. We start by choosing an attribute and we tweak slightly images with a GAN to generate small variation along a curve. We then project to the embedding space where we can compute by finite differences a normalized vector field where each tangent vector, here in red, represents the direction of infinitesimal variation for the chosen attributes. Each attribute, like hair color or age, is associated with a different vector field. Using this vector field, we will estimate the degree of invariance of the model to each attribute. Our intuition that we validate in the paper is that if a model is invariant to an attribute, the normalized vector field will look random because it would correspond to residual noise. On the other side, if the vector field is not random, like on the left, it reflects the predictability in embedding space of modifications to the underlying image. So the idea is to measure the randomness of the vector field, which is what the big epsilon function on this slide does. Concretely, we propose a method to quantify the degree of invariance of a model to different attributes. Here we illustrate this principle for some attributes and 3 face recognition models. The result of this analysis is a quantification of invariance model by attribute. Understanding invariance is important since it is related to biases, interpretability, and robustness. We anticipate that our work can be used to drive model selection and is not limited to face recognition contexts. Thanks for listening. If you're curious, come talk to Antonio at ICML or check out the paper.